and to the relationship of the net charge enclosed by that surface. Okay, so basically the electrical field and the inside the charge. Okay, Gauss's law considers a hypothetical imaginary closed surface enclosing the charge distribution, and the Gaussian surface can have any shape. Okay? It's not necessary to be a sphere, but well, could be any shape. Okay, but the shape that minimizes the calculation of the electrical field is the one that mimics the symmetry of the charge distribution. Okay, so well, theoretically, for the Gaussian surface, we can go to any surface, right? Something like this. But we want to minimize the calculation, right? So that usually we just use like some regular surface, such as the sphere, okay, such as the two parallel planes, okay, or cylindrical, okay. So I will give you some examples later. Okay, before our calculations, let's firstly talk about one concept called flux. Okay, okay. So for the flux, let's for example, we have the water flow. Okay, and the water flow has its own velocity. Okay, all the air flow. Okay, and it has its own velocity here. Okay, and then we need to consider there is a velocity going through a certain surface area. Okay, and then there could be different cases. The very regular cases is that the surface area is perpendicular to the flow. Okay, so in that case, we can define the velocity multiplied with the area as the flux. Okay, well, but we can consider another situation, that is the velocity has a certain angle to the area, but that is not a vertical. Okay, let's see if we make a perpendicular arrow of the surface area, then we can assume the angle between the velocity and the arrow is theta. And then in that case, if we want to achieve an equivalent flux, we should just say we can separate the velocity into two separate parts. One is along the surface area, another one is perpendicular to the surface area. Okay, so in that case, we can only consider the portion that is perpendicular to the surface area, right? This part, so that we need to multiply with a cosine theta term. Okay, so that in this case, if we define the vector that is perpendicular to the surface area, but the amount is equal to the surface area, then we have a new vector of the A. Okay, then the flux will be equal to velocity dot product of the area. Okay, and the flux is usually we use the theta as the flux of the air flow or the water flow. Okay, and well, for the electrical field, it is just similar, but what's the difference is just it's not the airflow or the water flow, it's the electrical field arrows. Okay, so that we can define the flux of the electrical field. But of course, we have talked about the Gaussian surface. But for the Gaussian surface, it's not necessary to be always like a flat surface, right? It is always like a curved surface. For example, like the heart shape. Okay, so that in this case, the flux of electric field passing through the Gaussian surface will be equal to a summary of many small areas. Okay, then in that case, we are cutting the Gaussian surface into many small pieces, and in each pieces we are having its own individual direction, so it has its own delta A vector, so that we can use the electric field multiplied with the delta V A actor and adding them together, and that's our the total flux. But of course, that's if we can also use the integral form. In that case, that would be dA and multiply with E and then integral. Okay, so as you can see, for each individual small surface, we can have its own direction of the delta A or dA and then multiply with the E. Okay. Okay, let's see for the chat question. What is the meaning of the circle with the integral sign? Okay, the meaning of the circle of the integral sign is because we want to integrate all over the surface of the enclosed Gaussian surface. Okay, that's a reason. Okay, it's not like we integrate from a certain area, but we are integrate all over the enclosed surface. Okay. Okay, let's see some example. For example, the flux going through the closed cylinder. Okay. Well, we have a uniform electric field which is pointing in the horizontal direction. Okay. And now we have a closed cylinder inside. Okay, now let's talk about what is the flux on each surfaces. Okay, and we have 3 surfaces for the enclosed cylinder. One is the curved surfaces, and the other 2 are the 2 disks on the 2 ends. Okay, but for the curved surfaces, you can see the electrical flux, electric field is parallel to the surface of the curved surface, right? So that in this case, we have the electrical field perpendicular to the dA, always perpendicular to dA, okay? So that's why, okay, anyway. Okay, and then in that case, what's happening? Okay, in that case, okay, there is no flux across the curved surface of the cylinder. Okay, and then we can calculate what is the flux going across the 2 disks. Okay, so for the left disk, the dA's direction, if we always we can always define the arrow of the arrow that is pointing out as the positive. Okay, so that we have the dA pointing out. Okay, and then we have the electrical field in the opposite direction. Okay, opposite direction on the left side. I don't know why I cannot use a pen here. Anyway, what's happening? Okay, let me restart the PowerPoint. PowerPoint sharing. Okay, on the left side, the electrical field still cannot write here. I don't know why. Okay, anyway, let's just continue. So on the left side, we have the opposite direction of the dA and the E, so that we will achieve a negative result. And then for the right side, you can see the electric field and the dA is in the same direction, so that we can achieve a positive result. Okay, so that well, in this case, we have the two flux. They have the same amount, but in a different direction, right? So that in that case, the overall electrical flux we will have is also the zero. Okay. Okay. Someone is asking, will this kind of integration will be taught in the course? I don't know what kind of integration. Okay, anyway, it's just the integration. Oh, you mean the integration with the circle? This is just the integration, but when it is over the enclosed surface, right? Enclosed circle or enclosed surface, then we can give a circle sign, but that's no special. It's just the integration. Okay, so don't worry about that. And why the dA in the opposite direction? It's because we always want the dA is pointing outside of the volume. Okay, so that the of dA in the two sides is in the opposite direction. Okay, so let me show you another example. The other example is a flux going through a closed cubic. Okay, so as you can see, there is an enclosed cubic. Okay. So that they have the 6 surfaces, and now we have a electrical field. Okay, and this electrical field has the distribution on both the x direction. You know, the I is actually x direction, and the y is actually okay. Let me show you this one. This one's better. Okay. I is actually x direction. J is actually in the y direction. For the I direction, x direction is actually not uniform. It's depending on the x, okay, 3x. And for the y direction, it's uniform. It's 4. Okay. Okay, someone is asking, is this cylinder hollow? Well, it's okay either way, it's hollow or not, right? It's just a Gaussian surface. We only focus about how much flux going through the Gaussian surface. So it's either way is fine. Okay, so there are no flux through the cylinder. Well, we are talking about flux through the surface. Okay, let's come back. We are talking about the flux going through the outer surface. We are not talking about we don't care about what's happening inside. Okay, what's happening inside will be explained by the Gauss's law later. Okay, anyway. Okay, so come back. This is a closed cube, and then we have defined what is the electrical field, and now we can calculate what is the flux going through each individual surfaces. Okay, so let's start. For the top surface, okay, top surface, if you can imagine the A is going upward, right? The A is going upward, and the area is 2 by 2, because this is 2 meter, this is also 2 meter, right? So that is 4 meters square. Okay, and also if you compare with this electrical field, there are someone going along the x direction, so that we just ignore that because that is in parallel with the top surface. We only consider that one is pointing to the y direction. Okay, and then the portion pointing to the y direction, the amount is 4, right? Okay, so that for the top surface, we have the 4 multiplied with the 4. We achieve the 16. Okay, this is the top surface's flux. And then the bottom surface. Okay, bottom surface is quite similar, right? We also have a 2 by 2 by 4 as the area. We also have the 4 as the electrical field. But what's the difference? You can imagine the A, the vector, is pointing down. Okay, it's going down. So that, but the electrical field is positive, going up. So that they are in the opposite direction. So in this case, the flux should be 4 multiplied with the -4. So we achieve the -16 for the bottom surface. Okay, and then for the left side, okay, left side, it is a little bit more complex because the electrical field is depending on the x position, but the area is still the 2 by 2 is 4. Okay, it's pointing left. Okay, and then we can focus, take a look at what is the electrical field. Okay, the electrical field is depending on the x, and now the x is 1 meter. So we put it inside, so the electrical field will be the 3. But this 3, you see, it is positive, so it is along the positive x, so it is going right. Okay, so the area vector going left, electrical field vector going right, so that we should have the 3 multiplied with -4, achieving the -12, okay, as a flux for the left. Okay, and for the right surface, okay, so we have the surface area still the 4, okay, and in this time the area vector going to the right, okay, which is along the electrical field, and then you can see for the electrical field it's still the 3x, but it's positive, okay. Then this time the x is 3, okay, so that we get 3 multiplied 3, we get 9 as the electrical field pointing the positive, and then positive, so that we get a positive flux. So that would be 9 multiplied with 4 equals to 36. Okay, probably you want to ask what is the this surface, right? The surface efficient to us, and the surface behind us. What is the flux here, right? The flux should be 0 here, right? That is because the area vector is along the z direction, right? But the electrical field is along the x direction or the y direction, right? So they are perpendicular to each other. So this surface and the surface behind us has a flux of 0. Okay, so that the other 2 surfaces are just 0. Okay, and then you can calculate what is the total flux over the enclosed cube. That would be 16 minus 16 minus 12 and 36. That will be 24. Okay, so let's see if you have questions. Someone is asking, could you explain again why values of bottom left surface are minus VE? Okay, so that is because if you consider what is the direction of the A, you know the direction of the A vector is always pointing outside. I don't know why the pen is not working in the PowerPoint. So let me switch to my whiteboard to see if it works. Okay, sounds good. PowerPoint is sometimes getting stupid. Anyway, okay, we have a cubic. Oh no, why? Okay, we have the cubic. Okay, so if you want to know what is the A on the left side, okay, that would be pointing this way, right? This is the A vector. And for the bottom side, it would be pointing this way. Okay, right? Okay, so and then for the electrical field, you know, let me show you the vectors. This is a y, okay. This is x, okay. Positive x and positive y. And for the electrical field, it equals to 3xi plus 4j, right? So that if you want to plot what is the electrical field is along somewhere here, right? Okay, so that as you can see, the electrical field has almost the opposite direction of the A for the left side surface, and for the bottom surface is also the opposite, right? So that if you are multiply with the electrical field on the left and the electrical field on the bottom, you will have a negative sign here. Okay, but for the other surface, you get a positive. Okay, so that's one question. Someone is asking why 9. Can you explain, please? Okay, that is because if you see the electrical field, it is it is 3x and I plus 4j. Okay, the reason it is 9 at the right surface is because at the right surface x equals to 3, right? So you get you put a 3 into here, so you get a 9. Okay. See, that's the next question. Why E equals to 3xi plus 4j instead of 3i plus 4j? Well, that's by just a definition, right? So the 3x means it need to depends on the coordinates of the x, right? Okay. So the next question. So is the surface area a cross product of the side of the cube? A cross product of the side? No, it's the length of the cube is not a vector, right? So it's not a cross product. It's just a product of the size of the cube, 2 by 2. Okay. Someone is asking why the 9 multiply 4 of the right surface. Can you explain again, please? Well, I just explained how could we get the 9, right? That is because the x equal to 3, and then it's a 3x for the electrical field. So the electrical field is 9, and then 4 is the surface area. Okay. Okay, I'm happy you are discussing here, but I hoping you can give you can always put in the chat for everybody, not just for me. Okay, so that the other people can see your question. Okay. And then the next question, why do we use the area to calculate by use 3x in the left, right? Well, that's by the problem, right? The problem says that along the x direction, the electrical field is 3x. Okay. Horizontal current. Okay, how do we get the 4 on the top surface? Okay, 4 by 4 is the electrical field is 4. And then the surface area is also 4, okay? Okay, I think you probably have already get it clear. Okay, let me switch back. Okay, anyway, you can re-review this problem again. And basically, for the first line, it is the electrical field on the product, okay? And the later one is actually the area, but the area should be given with a positive or negative depending whether the area and the electrical field is in the same direction. Okay, anyway. Okay, finally, we talk about the Gauss's law. Okay, so what is the Gauss's law? Let's see, we have the multiple point charges. In this case, there are 2, one is positive, one is negative. Okay, they have equal magnitude, and then we can define several 4 Gaussian surfaces S1. S2, S3, and S4. So as you can see, S1 is outside of the positive charge. S2 is outside of the negative charge. S3 is outside of nothing. S4 is outside of both. Okay, and for the total flux going through all these surfaces, we have the Gauss's law, which says about the total flux outside the Gaussian surface multiplied with the epsilon 0 equals to the total Q inside. Or the total flux can be replaced as this integration, okay, multiplied with epsilon 0 equals to enclosed Q. Okay, and then as you can see, we can make some judgment. Okay, the judgment is by the you can see the S1 is enclosed of the positive charge. Okay, so that there must be some total flux. Actually, you can see the flux through the electric field lines, right? For the S1, the electrical field lines are always going inside from the outside, so that there must be a positive flux. Okay, and then S2 is the electrical field lines are always going inside, right? So in this case, there must be a negative flux. Okay, and then there is a negative charge inside. Okay, S3 is inside is nothing, and then there is always electrical field going inside, and then the same amount going outside, so that the S3 has a 0 total flux. S4 is more complicated. That includes one positive charge and one negative charge. But then, if you calculate how much the positive charge is the flux line going outside, and the electrical field line going inside, you will see it's also the same. So that that would be the 0 total flux over the S3 and the S4 as they as they enclose the 0 net charges. Okay, and then we can see if the enclosed charge is positive, the net flux is outward of the Gaussian surface. If the enclosed charge is negative, the net flux is inward of the Gaussian surface, right? Which can be judged just from the electrical field lines. Okay, let's see the questions. Okay. Someone is asking me, okay, again, if you want to say or ask something, I suggest you send it to everybody so that other people can see your question. Okay, someone is asking the other side flux is equal to 0 because the direction is perpendicular. Well, I'm not sure which one you are talking about. If the electrical field and the surface is parallel to each other, okay, or in another word, if the electrical field is perpendicular to the surface vector, okay, A, then in that case, the flux should be 0, right? Because that is not penetrating in the surface, okay? Then what are the units of the flux? The units of flux is just the electrical field of units multiplied with the area of the units, right? So that would be, I would say Newton per Coulomb multiplied with meter square. Okay. And is it mean no charge means no net flux? That's true. If there's no charge inside the Gaussian surface, there's no net flux, right? 0 net flux. It's not no net flux. Okay. Anyway. How can we see the figure? Is it a 3D model? I'm not sure what you are talking about, but in the real situation, it's a 3-dimensional. Okay, so what we show is just a 2-dimensional figure, but it's actually a 3-dimensional. You can imagine that. Okay, what is the flux of S1 and S2? Okay. Well, flux of the S1 is apparently positive, right? S2 is apparently negative. Okay, and well, you can really calculate that, but you can just estimate through the electrical field lines, right? Because it's pointing out, then that's positive. Pointing in, that's negative. Okay. And how about the line in the middle? I'm not sure what you are talking about. Okay, so probably you should give a more complete question. Okay, in the middle, it's still you need to judge whether it is going penetrate the electrical field. No, the Gaussian surface, right? So if you penetrating the Gaussian surface, that can make a flux. If it's not penetrating, it will not make any flux. Okay. The law applicable to any shape or area. That's true. Okay, that's why it's a law. Okay, and it's so the flux in 3 is 0. That's true. Okay, 3 and 4 are 0. Okay, and 1 is positive and 2 is negative. Okay, let me show you another example relating the net, the closed charge and net flux. Okay, so we have 5 plastic objects with an electrical charge. Okay, 1 coin with no charge. Okay, 5, Q1, Q2, Q3, Q4, Q5. Q1, Q4 is positive. Q2, Q3, Q5 is negative, and then with a coin. Okay, and then we can make a Gaussian surface S by this shape. Okay. And then we have the Q1 equal to Q4, which is positive 3.1. Q2 is Q5, which is negative 5.9. And Q3 is negative 3.1. And then calculate what is the net flux going through the S. Okay, so for the net flux, we can just use this Gauss's law, right, which equals to the enclosed charge over the epsilon 0. Okay, so that would be the Q1 plus Q2 and Q3. Q1, Q2, and Q3. They are adding together, okay, and then multiply with the epsilon 0, and then you get the final answer. Okay, as you can see, from this Gaussian surface, the total flux is only relevant to the enclosed charges Q1, Q2, Q3. It's not relevant to any other things that is not taking charge. For example, the coin. It's not relevant. Okay, and it is also not relevant to any charge outside. Okay, so it's not relevant to Q4 and Q5. Okay, so in this case, you only count all the charge inside, and that's it. Okay, and then example 4, which is still the cubic, okay, in the non-uniform field. Okay, from a previous example, we have already calculated what is the flux on each surface, right? Still remember, right? Let's come back to this page, right? Okay, then let's come back here to calculate what is the total flux across in the Gaussian surface, okay, which is basically adding all the flux in the different surfaces, 16, minus 16, minus 12, and positive 30, 36, that's 24, okay? And then we can calculate what is the enclosed charge inside the cube, okay? That would be the enclosed charge equals to epsilon 0 multiplied with the flux, okay? And then we just put the number, then we can calculate how much charge you have. Okay, let's see for the questions. Q4, Q5 is not in the domain, but so need to consider it. So don't need to consider it, right? So not inside the Gaussian surface, so we don't need to consider that. Okay. Well, if you say the Gaussian surface is a domain, that's fine. Okay. Anyway, why the coin is not included by the charge, right? We already say there's a coin with no charge, so that's not contributing to any net flux. Okay, so is the charge, it means the charge in the surface. I mean the charge is the charge inside the Gaussian surface. inside the Gaussian surface. Okay. Okay, so let's continue. Gauss's law and the Coulomb's law. Okay, so this is the derivation from the Gauss's law to the Coulomb's law. Okay, so we can do the derivation. Then we can have a point charge Q. Okay, could be positive or negative. Anyway, it's positive in this case. And then we make a spherical Gaussian surface centered on the point charge Q. Okay, then we can have an aerial vector dA at any point perpendicular to the surface and directed outward. Okay, you know if you want to have a dA here, then you always have the dV pointing outside, right? And then because it's positive charge, the electrical field outside is also pointing outside. Okay, then we can calculate. Okay, we can write the Gauss's law as the epsilon 0 multiplied with the integral of E multiplied with dA. Okay, then that would be epsilon 0, okay, E dA, because they are in the same direction, right, equals to enclosed charge. Okay, and also for this surface, this is spherical surface, the radius or the distance between the dA and the Q is always the same, equals to the radius, right? Okay, so that the electrical field is actually a constant. Okay, so that we can take the electrical field outside, then that would become directly the integral of the area, the area. Okay, so you know what is the surface area of the sphere, right? Okay, that's a 4 pi r square. Okay, 4 pi r square. Okay, then that would be epsilon 0 E 4 pi r square equal to 0. Okay, then we can solve what is the E. That would be 1.4 pi epsilon 0. This is actually the K, right? And then Q over the r square. That would be the Coulomb's law. Okay, so that is from the Gauss's law, we can derive what is the Coulomb's law. Okay. Oh, you know, okay. Anyway, okay, let's talk about another very interesting property of the conductor. Okay, you know, we already talked about the conductor. In the conductor, the charge can feel free to go anywhere, right? So in that case, we have some special property. We have an isolated lamp of the copper hanging from an insulating thread and having an excess charge Q. Okay, so the Q is on the copper, and also it's hanging from the insulating thread. That means the charge will not go away from the thread. Okay, and then we can have a Gaussian surface, which is placed just inside the actual surface of the conductor. Okay, so the black line is the Gaussian surface, as you can see. Okay, and the reason we do that is because the electrical field inside the conductor must be 0. Why? Because in the conductor, the charge can freely moving, right? Why is that? It's because imagine you have a very small electrical field. So what will induce, right? It will induce the charge moving from one side to another side, right? Electrical field is like the driving force, right? Electric field will make a force on the charge, right? So it will move. And then the new charge will compensate the electrical field to make the total electrical field as 0. Okay, it's just like okay, when you have water, right? When you want to shake it, the shake it is like you have some gravity field around the water, and then eventually the water will be with the flat surface, right? So that is like no gravity field here. There, okay, so it's the same for the electrical field. Okay, so no electrical field inside the conductor. And then if you do the Gauss's law, right, then you integrate all the electrical field with the A to calculate what is the flux over the Gaussian surface. That would also be the zero, right? So that because the total flux going through the Gaussian surface is zero, so that the charge inside the Gaussian surface should also be the zero, right? So that inside this Gaussian surface, there's no charge. But as I said, that has already been an excess charge on the copper. So why is this charge Q? Okay, this charge Q must be lie on the actual surface of the conductor, on the outside, very, very outside. Okay, so that's actually a very special property of the conductor. Okay, so for the conductor, the charge are always on the outer surface. Okay, and let's see another example. If we make a hole inside, what should that happen? Okay, let's see. We call it a cavity. Okay. Well, if we make a cavity, we can make a new Gaussian surface, which is also along the surface, but it's inside the copper. Okay. So and similarly, we should have the zero electrical field, right? It's still inside the copper body, right? So that no electrical field, and then zero Gaussian flux across the Gaussian surface, so that zero charge on the inside the Gaussian surface. That means not only inside the copper there's no charge, in the inner wall of the copper, of the cavity wall, there should also be no charge, right? So the excess charge must always be in the outer surface of the conductor. Okay, no inside the conductor, no inside the inner wall of the conductor. Okay, so this is actually set the fundamentals for the electromagnetic shielding, right? So imagine if you are putting your cell phone inside a metal box, can you still receive the signal? The answer is no, right? Because the metal box has the electrical field, electrical shielding. Okay, why it has the shielding? That is because the charge must always stay outside, so that the electrical magnetic waves cannot go inside anymore. Okay, so that's a very special property for the conductor. Okay, so let's show you another very important example for the Gauss's law. Okay, a charged isolated conductor, and then what is the electrical field? Okay, so as we have known, for the conductor, the charge must always be on the outer surface. Okay, so let's see if we have a metal which is here. Okay, and this is its outer surface. Okay, so what is the electrical field outside of the outer surface? Okay, then we can make a new Gaussian surface. Okay, by the cylinder. Okay, in the cylinder, there is a half of the cylinder is inside, half of the cylinder outside. Okay, and the curved surface is in parallel with is perpendicular to the surface. Okay, so the two disc is in parallel with the surface. Okay, and then the A vector is pointing outside. Okay, and so that for the curved surface, we don't need to calculate what is the total flux, because the total flux is zero in the curved surface. And in the left disc, the electrical field is zero because it's inside the conductor. Okay, so we only need to consider the electrical field flux on the right disc. Okay, because it's the outside, we have electrical field pointing up, area pointing up. Okay, so that we have the epsilon 0 EA equals to sigma A. Right, EA is the total flux of the E here and A here. Okay, then epsilon 0 equals to sigma is the charge density on the surface and the area. Okay, then we can solve what is the electrical field, which is equals to sigma over the epsilon 0. Okay, so that would be the electrical field outside of the conductor. Okay, so it's only related to the surface charge density outside of the conductor. Okay, it's already 3:15, so we can have a break. And I will come back at 3:30. At the same time, you can continue to ask a question. Okay, someone is asking why there is a flux on the external surface only. Well, that is because we only focus on the flux on external faces only, right? Because the Gauss's law says for the Gaussian surface, the total flux is related to the charge inside, right? So that only the flux in the external surface matters, okay? And then question is the sigma means the charge per unit area of the conductor surface. Yes, the answer is yes. Okay. Okay, someone is asking why electric field inside the surface is zero. Okay, that's not a inside the surface zero. Is for a metal or for a conductor. Okay, any location, the electric field in any location inside is inside the conductor is zero. Okay, it's not tend to be zero. It's just a zero. Okay. Except in the surface, if it is inside the conductor, as I said, if there is any electric field, it will generate forces on the local charges, and then charge will move. After the charge move, the electric field will be compensated, right? So that the total electric field will be balanced at zero. Okay, it's not a weaker, it's just a zero. Okay, if it is a conductor, then it's a zero. Okay, so let me continue. Okay, we have another example, a spherical metal shell. What is the electrical field? Okay, so if we have a point charge of -5 microcoulomb located as R/2 of the center. As a result, the positive charge is non-uniformly distributed on the inner wall, and an equal amount of negative charge is distributed on the outer wall. Okay, the reason we have positive charge is because it's a attractive positive charge inside, right? And then we have a negative charge left over on the outside. Okay, and the reasoning is there is no electrical field in the inside the metal. All right, so that there is no electrical flux. If we make a Gaussian surface, okay, Gaussian surface of the red circle. Okay, so there is no electrical flux along the Gaussian surface. Okay, so therefore a positive charge of 5 microcoulomb must be on the inner wall. Right? It cannot go inside of the metal, right? It can only go to the surface, right? So that the total charge must be zero. Why? Because the Gaussian surface the flux is zero, right? So that the positive charge must be also 5 microcoulomb, and it's also on the inside wall. Okay, and the point charge is off center, and then to compensate for the electrical field induced by the point charge induced by and the charge on the inner wall must non-uniformly distributed, right? There's a little bit higher density here, lower density here. Okay, and then since the shell was electrically neutral, that means the total charge on the shell is zero. Okay, then the outer wall must have the charge of the -5 microcoulomb. Okay, and then note that the point charge and inner wall charge together induce no electrical field to the conductor, right? Because the inside the conductor there's no electrical flux, so that in order for the charge on the outer wall to induce no electrical field in the conductor, the charge must be uniformly distributed on the surface of the spherical shell. Okay, so that's actually a case of the shell. But as you probably are wondering why we also induce the charge in the inner wall. That is because there's a charge inside, right? So when we say there's no charge in the inner wall, that's because no charge inside. Right? If there is a charge, we still induce the charge in the inner wall. Okay, but anyway, the key point is still in the Gaussian surface. There's no electrical field. Okay. Okay, so let's see another cases for the Gauss's law. We just say a cylindrical for the surface, and just say for the point charge, and say for the Gauss's law for the cylindrical symmetry. Okay, for cylindrical symmetry, we can use that for a plastic rod. Okay, and this rod is, you can just think it is a line. Okay, and then it has a linear line charge density of lambda. Okay, you still remember the lambda, right? Charge per meter. Okay, and then we want to know what, and this is infinite long. Okay, and we want to know what is the electrical field going outside. Okay, let's see. We can make a cylindrical shape outside of the line charge. Okay, so that we can calculate what is the total flux outside of this Gaussian surface. Okay, firstly, we should confirm the electrical field is always going outside. Okay, they are parallel going outside. Why it is parallel? That is because it is infinitely long, right? So that if the one electrical field line is not parallel, in that case, it's not symmetric anymore, right? So it must be parallel, and then it's going outside. Okay, so that we can imagine for the curved surface, there must be a positive flux. Okay, but for the two disks, there should be zero flux. Okay, so that we can calculate how much the total flux outside of the curved surface. Okay, so we use this Gauss's law, epsilon 0 phi equals to Q enclosed. Okay, the phi is just indicating the curved surface. Okay, and then also you can see all the electrical field, if they are always pointing outside, you can see it should be always perpendicular to the curved surface. Okay, so that you can directly just use, and also the electrical field outside the curved on the curved surface, the amount should be the same, right? So that you can just take the electrical field out and then calculate how much the total area on the cylindrical shape for the curved surface, okay, which is 2 pi r multiplied with the h. H is the height, r is the radius. Okay, and then multiply epsilon 0 equals to lambda h. Lambda is the charge density, and the h is how much charge inside. Okay, then you can solve that to achieve the lambda over the 2 pi epsilon 0 r. Okay, so that's the Gauss's law to calculate what is the electrical field outside of the cylindrical rod. Okay, and then we also can use this Gauss's law to calculate the electrical field outside of the planar symmetry. Okay, so this is actually different from the conductor's surface. The conductor's surface says, okay, we have the surface charge outside of the conductor. We want to calculate how much electrical field. So what we talking about here is infinite non-conducting sheet. Okay, sheet is just means just one plane with just like a paper. Okay, and in this paper they have two surfaces, right? Okay, and there is a charge density, average charge density of sigma here. Okay, so that if you build a cylindrical shape for the Gaussian surface, right, you need to consider two disk surfaces. They both can have the flux. So let's see this cross-sectional area. So apparently for the curved surface, there is no flux, right? Because all the electrical field outside, considering it is infinite, they should be all parallel. Right? So this is always parallel to the curved surface. Okay, and then there's no flux on the curved surface. For the two disks, okay, electrical field is going outside. Okay, on the left going left, on the right going right, and the A of the disk is always going outside. So on the left going left, on the right going right, so that the electrical field at distance r equals to epsilon 0 multiplied with the flux. Then the flux has two components. One is on the left one is on the right, so that's EA plus EA, okay, which equals to the enclosed Q, and the area, the Q will be the area multiplied with the charge density sigma, so that's the sigma A, okay, and then we can solve that. That would be the sigma over the 2 epsilon 0. Okay, so we can make a quick comparison with the previous result of the metal surface. Okay, sorry, go to wrong place. Right, so you can see this is a sigma over epsilon 0, but something wrong with okay, so this is actually sigma over 2 epsilon 0. Okay, why? That is because for the previous example, the electrical field cannot go inside, right? But for this example, the electrical field going in both sides, right? Previously, we are saying what is the electrical field outside of surface. This is the electric field outside of the non-conduction sheet, right? A paper, just a plane, okay? So that actually makes the difference. Okay, let's consider another special case, okay? Applying Gauss's law for planar symmetry when we have the two planes, okay? One is taking the positive charge, one is taking a negative charge, okay? So, well, for the two infinite plane, if we are seeing one infinite plane, they have the charge density, but the charge density is distributed on the both sides, so that let's see if it's a sigma 1 on the surface, okay? So that the electrical field outside would always be sigma 1 over epsilon 0, okay? It's going outside, okay? But for the negatively, the electrical field will be pointing inside, okay? Then the question is, what is the electrical field in the left region, in the middle region, in the right region? Okay, let's see. If we have calculated for the left region, the electrical field induced by the positive sigma 1 is a sigma 1 over epsilon 0, but pointing left. Okay, induced by the negative sigma 1, it's the same number, right? So this electric field is a constant, it's not decay with the distance, okay? Anyway, so, but with the same number, but it is pointing left, pointing right, okay? So these two are cancelled, so outside is 0 electrical field. Similarly, here is also 0 electrical field on the right, but in the middle, they have positive electrical field pointing right. They also have the electrical field pointing right. So these two are adding together. There will be 2 times of epsilon sigma 1 over the epsilon 0. Okay, so that's actually one way. That's another way, okay, to calculate this problem. Imagine these are the 2 conducting plates. Okay, you know, for the 2 conducting plates, we have the charge freely moving on any location to the inside the conductor. Okay, so that all the positive charge was concentrated on this surface. All the negative charge was concentrated on this surface. Okay, then so that the charge density was doubled, become like a 2 sigma 1. Okay, and then if we calculate what is the electrical field inside, right? So that we can build a Gaussian surface, right? Just like what we build for the conductor surface, right? So that on the left side, there's no electric field. We only consider electric field on the right, okay? So that you will achieve the 2 times of sigma 1 over epsilon 0. Okay, you can also rewrite the 2 times of sigma 1 as the sigma, because this is the resulting final charge density, right? So that you can achieve a final electrical field equals to E equals to sigma over the epsilon 0. This is actually talk about what is the electrical field inside the parallel plate-based capacitor. Okay, we can continue this derivation in the following sections and talk about when we are talking about the capacitance. Okay. Okay, so we talk about the line, the cylindrical symmetry, the plane symmetry, and then we also have the spherical symmetry. Okay, well, this is just similar to the Coulomb's law, but let's get to review again. The thin uniform charges the spherical shell with a total charge of the cube. It is distributed as here. Okay, the dashed lines. And we have the two Gaussian surfaces. One is S1, one is S2. But the S1 is inside, S2 is outside. Okay, and then let's see what is the total flux of the S1 and S2. And apparently, there is no charge inside S1, right? So that the total flux on the S1 is 0. And then the electrical field is 0, okay? So that for a shell with a charge distributed outside, okay, there is actually no electrical field inside the shell, okay, when the R is smaller than big R. Okay, for the outside of the shell, okay, you can have the enclosed charge of the cube, right? And then you can use either the Coulomb's law or the Gauss's law to calculate the electrical field, and then the electrical field is equal to this one. Okay, so this is for the small r larger than the big R. Okay, then to the outside, it is as if the shell's charge were concentrated at the center of the shell. Okay, this is actually also a demonstration of the shell theorem. Remember, we talked about the shell theorem without prove it, right? This is actually kind of like a prove it, right? Because we have a better way to prove it. Okay, and then there is no electrostatic force on the charged particle inside the shell because there's no electrical field. Okay. All right, so this is the Gauss's law. Basically, this is the most important law for the electrostatics. Okay, and then let's go to the next topic about the electrical potential. Okay, so probably you have learned what is the potential energy, right? When you have the gravity, you have the gravitational potential energy, right? You have, when you are in the higher height, you should have a more gravity energy compared with the location when the height is smaller, right? And similarly, for the electrical field, you have that. Okay, and the reason they have the common property is because they are both conservative forces. Okay, the conservative force is a force that is the property of the work done in moving a particle between the two points is independent of the path taken, right? So if you are moving a higher location to a lower location, right, you can go this way or go the other way, but the change of the energy is the same, right? So that the work done is the same. Okay, so that's why I call it conservative force. And as a comparison, it says a non-conservative force. For example, the friction, dissipative force. Okay, friction or any resistance or any damping in the spring, that's dissipative. Okay, so the dissipative, that means the energy was converted to another form, but that form cannot transfer back, right? If it goes through the friction, it becomes the heat, and the heat was dissipated anywhere, so it cannot become the mechanical energy again, right? So that's a dissipative or non-conservative. And the conservative means it can be converted to any kind of like a potential energy. If it's gravity, go to the gravitational potential energy and convert it between the kinetic energy, and then it can be converted back, right? And also similarly, the electrical energy electrical force can make a conservation and between the electrical potential energy. Okay, so that the electrical force should be associated with electrical potential energy, and it is convertible. Okay, and then the motivation for associating with potential energy with a force is that we can then apply the principle of the conservation of the mechanical energy to close the system involving the force, so that a lot of calculations or a lot of derivations would be much similar. Okay, so that we can use the conservation of energy. Okay, so what is the electrical potential energy? Okay, so when an electrostatic force, okay, for example, the force from the Coulomb's law, right? Okay, when the force acts between the two or more charged particles within a system of particles, we can assign an electrical potential energy U to the system. Okay, and if the system changes its configuration from the initial state I to a different final state of F, the electrostatic force does work W on the particle. Okay, and then if the resulting change is delta U, then the delta U equals to U final minus U initial equals to minus W. Okay, the reason we say it is a minus W is because this work W was done by the electrical force. Okay, so it's like the force is giving a W outside. Okay, so that it should have a minus sign when we say the delta U. Okay, and now if we can set at the U initial at 0 and infinite as our reference potential energy. Okay, usually we set with the infinite location as the reference potential energy, or another alternative way is setting the ground. Okay, but in fact, for any location, we can set the potential energy as 0. Right? It's just like for the gravity energy, you can set at any height to be 0, right? And then above it is positive, below it's negative, and that's it. And the only thing that matters is the difference between them, because that determines how much work we need to have. Okay, sorry. Okay, so and then we can define what is the electrical potential. Okay, so the potential energy is actually related to the charge at a point. Okay, and then the ratio in the electrical field is called the electrical potential V. Or simplify, we can just use the potential at that point. Okay, so this is a scalar quantity. Okay, or we can say it's just a V equals to U over the Q. Okay, U is the energy. Okay, Q is the Coulomb. Okay, V is well, we will talk about the unit later. Okay, and then we can calculate what is the electrical potential difference V. Okay, between any 2 points, the I and F, in an electrical field, which is equals to the difference in the electrical potential energy per unit charge between the 2 points. Okay, delta V equals to V final minus V initial. Okay, and then it will be U final over Q minus UI over Q equals to delta U over Q. So that's a minus W. W is work over the Q. Okay, and then if the UI is 0, okay, and then the electrical potential V must be also be 0 there. Okay, so the VI is also 0. So that in this case, the V is equals to minus W infinite over the Q. Okay, well, the W infinite is the work done by the electrical field on a charged particle as the particle moves from the infinity to point F. Okay, from this equation, we can actually calculate what is the electrical potential on any location in an electrical field. Okay, And also, there is another important thing is electrical potential difference of delta V. This can also be called a voltage. Okay, the reason is use V is also because it's voltage. Okay, so voltage is the potential difference. Okay, so when you are seeing a battery has a voltage of 1.5 volts, that's because the potential difference is 1.5 volts. Okay. Okay, let's talk about the units of the electrical potential. The SI unit for potential is the joule per coulomb. Okay, and or alternatively, it can be called as the volt, V-O-L-T, or by just using the V. Okay, the relationship between the unit of the electrical field is 1 Newton per coulomb, right? 1 Newton per coulomb, which equals to 1 Newton per coulomb multiplied with the V multiplied C over the joule, and the joule over the Newton meter. Okay, so this is from the voltage. This is from the mechanical energy input, so that we get a joule and joule get over, coulomb and coulomb get over, and Newton and Newton get over. So eventually we have the volts per meter. Okay, and also for the atomic level, also subatomic level, right? When everything is very small, usually we use another unit. It's called for energy is electron volt. Okay, electron volt is not a volt unit. Okay, it's actually for energy. Okay, which is equals to the work required to move a single elementary charge E, for example, electron or proton. So a potential difference of exact 1 volt. Okay, so that would be equal to 1 eV equals to 1.6 multiplied 10 to minus 19 coulomb, which is the charge of the electron. Okay, so this is the charge of electron multiplied with 1 volt. So you achieve the 1.6 multiplied 10 to minus 19 joule. Okay, so that's 1 eV. Okay, so let's say the work done by an applied force. Okay, if a particle of charge Q is moved from point I to point F in an electric field by applying a force onto it, the applied force does work WAPP on the charge, while the electric field does work W on it. Okay, then the change K of the kinetic energy of the particle, there are two work. So one is by the applied force WAPP. Okay, another one is by the electric field W. Okay, so that we can say the kinetic energy change equals to WAPP plus W. Okay, but here if the particle is stationary before and after move. Okay, probably you have heard the quasi-static moving. Quasi-static moving means before the moving, after the moving, and around the moving, all the charge are almost in static, are almost with no kinetic energy, right? But that's impossible, right? You must have a certain velocity to move that, right? But well, we can just imagine that the physical meaning is we are not consuming some additional energy, right? If you are having some increased velocity, you need to have the acceleration and you have some consumer energy, but we are avoiding that, right? We are just using the exact energy without the consumption, additional consumption. Okay, so let's say if this is a quasi-static, then the delta K is 0. Right, the velocity is not changing. So that then in this case, WAPP equals to minus W. Okay, because they are adding together is 0. And then relating the work done by our applied force to change in the potential energy of the particle during the move, when you should have the delta U equals to WAPP, because previously we said WU Yeah, WU equals to minus W, right? And now it minus W equals to WAPP, so that equals to WAPP, okay? We can also relate the WAPP to the electrical potential difference delta V between the initial and final locations of the particle, right? So that would be the Q delta V, right? Q delta V is actually delta U, which equals to WAPP. That means, okay, the work done by the applied force to compensate the electrical field can make the change of the potential, electrical potential. Okay. Okay, so then there is another concept, equal potential surface. Okay, so when we have the adjacent points, they have the same electrical potential. That would be an equal potential surface. Okay, here are some examples, right? For example, the rotor 1, we are moving along the equal potential surface, right? Then in that case, the initial potential is zero, as same as the final potential. Okay, in that case, there will be no work done, right? Why? Because of this one, right? Delta V is 0, the WAPP is 0. Okay, and secondly, for the second road, we are jumping from one equal potential surface to another one, and then jumping back. But in this case, even the road is different, but the delta V is still 0, right? So there is no net work was done. Okay, they could make a positive work first, and then negative force work second, but the total work was done is 0. Okay. Okay, let's see another road 3. We have the particle jumping from V1 to V2. Okay, straightforward. And the road 4 is still also from the 1 to 2, V1 to 1 2. But that is like a jumping from V1 to V3 first, and then jumping back to V2. Okay, in this case, the work done is same for those 3 and those 4. Why? Because the delta V for these two cases equals to V1 minus V2 is the same, right? So that the work APP would be the same. Okay. Okay, so these are just the conceptual for equal potential surface. Let me show you some real examples. Okay. For example, we have the the uniform electrical field here. What is the equal potential surface? Okay, as shown as the dashed line. Okay, if we have the electrical field outside of point charge, we have the equal potential surface, something like this. Okay, if we have the 2-point charge, the dipole, it will be also like a surface, okay, outside like this. And probably you have noticed that the equal potential surface is always perpendicular to the electrical field. Okay, why? Right? And that is because you can see, okay, if you are moving a particle that is always perpendicular to the electrical field, right? In that case, there's no work done. Why? Because if you want to have the work done, you should have force first, and secondly, you have the force. Under the force, there should be a displacement made along the force. Okay, that's why we use the dot product of the F multiplied with the displacement. But in this case, if you are moving that perpendicular to the electrical field is always pointing to one direction, but your moving distance is always in another direction, right? So that the force and the distance have a dot product together is 0. Right? So that in this case, there's no work done. No work done means you are along the electrical potential surface, right? So that the equal potential surface is always perpendicular to the electrical field. Okay? Okay, that's one thing. And another property we can think, if we are moving along the electrical field, will we have the increased the potential or decreased potential? Okay, we must have the decreased potential. Why? Okay, because if we are along the distance, that means the work done by the electrical field is always positive, right? If imagine it is a positive charge, okay, then the force is along the electrical field, the moving distance along the electrical field, so you are making a positive work by the electrical field. So that if you want to compensate this work, you should have an additional work to be negative on it, right? So if you have a negative WAPP, then you have a negative delta V, so that you are moving to a potential which is lower. Okay, so that is a very quick judgment that the electrical field is always pointing from a high potential energy, higher potential to a lower potential. This is a high potential. This is a low potential. Okay, so remember that. Sometimes during problem, you probably get confused. Oh, there's so many positive sign, a negative sign. I get confused with my calculation. This is one way you can check, okay, whether you are doing right on the potential change. Okay. Okay, let's say some real example. Calculating the electrical potential from the field. Okay, so let's see if we have a pointer charge Q0 moving from the point I to the point F, I and F. Okay, so the dW equals to F dot product of the ds. Okay, so it's a dot product between vectors, so that you need to consider its direction. Okay, of course the F is along the electrical field. Okay, QE. Okay, and then for the total work, we can use the Q0 taking outside and the integral of the E and dot product of ds together. Okay, so that this W is actually, it's made by the electrical field, so that it would be equal to V F O minus VI, but minus with an additional minus sign and E ds. Okay, so this is actually the equation to calculate the potential change along when the charge was moving along the electrical field. Okay, as you can see, along the electrical field, you are also making a negative delta V, right? That means you are also pointing from the positive V, a higher V to a lower V. Okay, so remember, this is very important for the judgment. Okay, and also since the electrostatic force is conservative, all the paths should yield the same result. Okay, so you don't need to care about which path you go. So you go this way, you go this way, you get the same result as long as you have the same final and initial positions. Okay, let's see example 1. Okay, we have the uniform electrical field. That's always the simplest case. Okay, and then we find the potential charge from the electrical field, potential change from the electrical field. Okay, and the moving path is just along the electrical field. Okay, very simple case. Okay, well, we can just use the equation V final minus Vi equals to minus integral of electrical field and ds. Okay, and equals to minus Ed. Okay, well, let me finish this okay, and then anyway, so the final result would be the minus ED, because I just see some questions previously I didn't say. Okay, sorry, I missed so much questions. Okay, let me see. Can you explain the upper one again? Okay, probably you should specify the page because we have gone so too much. Can you explain page 646, the last equation again? So let me go with this one first. 46. Okay, you mean this equation, right? So so this is actually calculation how much electric field in the middle. Okay, so assume it is a conductive two plates. Okay, so that the charge was always attracted here. Okay, so that the charge density becomes 2 sigma 1. Previously it's like this. Okay, so each surface has sigma 1. Now it's concentrated, it's 2 sigma 1. Then there is electric field between the positive and negative charge. Okay, but what is the electric field? Okay, we can build, probably I should remove this first. Okay, we can build a Gaussian surface, something like this. Okay, on the left side, no electric field. It's inside the conductor, no electric field. Okay, no flux. On the side surface, there is electric field parallel, no flux. Okay, only flux is on the right surface, right? On the right surface, the flux is EA, right? And then epsilon 0, okay, which equals to 2 sigma 1 and then the A. Okay, then you solve the E, you achieve this. Okay, so that would be the electrical field in the middle of the two conducting parallel plates. Let's see, another question. Why negative? Probably you should have specified again which page is in. From the high potential to low potential, you get IVE. From high potential to low potential, not sure what you are talking about, so we can get to that later. How come ED? You mean this one? Okay, that is because the electric field integral with the rod, right? The rod total length is d, and they have the same direction of the ds and the E field, so that it becomes just simply multiply together. So that's ED and minus. Okay, page 57 ED minus ED, I just talked about. Why VF minus VI equals to minus ES? Not this page. Oops. Okay. Oh, page 56, sorry. So are you asking why it is a minus sign, right? I guess you are asking the minus sign. Okay, so because this W is the work done by the electrical field, okay? But let's come back to this page, right? The W means the work done by the electrical field, okay? So the W can be can be the integral form. Okay, the integral, the E ds. Okay, with the q0. So this equals to this one. Okay, but if you want to move the charge in the electrical field, you actually use some additional force, right? Then the additional force will make the work of WAPP to compensate the W, right? So that the work APP is equals to minus W, okay? Then it equals to minus Q the integral, okay? At the same time, the work APP as we derived equals to QW delta V, right? So that the Q and Q get cross, so that it will be W delta V equals to minus integral of E and ds. Okay, that's the minus sign coming from. Okay, so I hope you have already get clear with that. Okay, so it's already the time. Sorry for missing the questions. I don't know why that's not a notification on the top. That previously that's a notification showing that's an additional chat, but now it is not. I don't know why. Okay, anyway, so see if you still have questions, we can still talk about questions, and otherwise we will finish and see you on Thursday. I think email the recording to you is fine because we have the 2 sessions. One is Monday, Wednesdays for A. One is Tuesday, Thursday for BC. Okay, sometimes the progress has a little bit of difference, right? So that if we send the link directly on the Blackboard, sometimes students get confused, right? So whether it is my session or not, right? So that's why I instead with sending you the email. Okay, so if you have difficult, for example, you missed some emails accidentally or something, you can just email me and requesting for the record link. So that will be the same. Okay. Won't get confused, right? I don't know. I think it's the best way. Anyway, any technical questions? I think in the Zoom it's also okay, right? You just log in and you can see it. You should check. So you check it every check the email like every hour. We check. We should. If you Outlook is back, download some email software in your cell phone, and then you can find the email link, and then you can take it. And believe you, if you are taking a look at the video, you should always check. It's best to check the computer, right? And then in the computer, you should always check the email. I don't think it's a problem. Not sure which technical problem, but anyway, if you still think it's a big problem, you can still email me. And I don't know. I actually didn't get why it is bad on the Zoom. And also, if it is on, I think what I will do is still sending a link, right? So you will still see the in a room. No difference.